So I hope you all have had a great spring break. Before the break, we talked about Dirac equation. So we introduced the equation. We showed that it is Lorentz covariant. And then we started talking about the classical solutions of the Dirac equation because finding the complete set of solutions for Dirac equation is the necessary step for quantizing it. Okay, so let us continue. Consider the classical solutions. Of Dirac equations. And recall the Dirac equation is given by the following. Okay, so this gamma matrices, these gamma matrices are 4×4 matrices, and psi is a 4-complex vector. And we already know, just from setting up the Dirac equation and the properties of the gamma matrices, that this should have solutions proportional to, say, plane wave with k squared, say, equal to minus m squared. Okay. So our goal is to find the prefactors. Okay. So here we separate into two kinds of solutions. So this just reminds you, we discussed at the end of last lecture. We call UK corresponding to the positive. So we always take K to have positive time component. Okay, and so this is the positive energy solution. Then we have also so-called negative energy solution. So these are just names. Okay, it does not really means that they have positive energy or negative energy. Okay, just means the sign here. Okay. So now if you plug this into the Dirac equation, and then you get the algebraic equation for U. You get the algebraic equation for U, and then you find ik slash m u equal to 0. And ik slash plus m v equal to 0. Okay, so u and v satisfy those equations. Okay, and so I suppose you're already familiar with the notation. Say this k slash. Okay. So those equations, in principle, you can just solve them. Okay, so these are just linear equations, and in principle, you can just solve them. But still, there are tricks how we solve them. Say so that it's mostly transparent. So there are two methods of finding the u and k. So one method is we first go to the rest frame. Say we take k mu, say to have 0 spatial momentum, and then the k mu will be just equal to m0. Okay. So in this case, those equations become particularly simple, and also before we solve them, actually we should also specify the gamma matrices we need to use. So the gamma matrix we need to we will use is given by the following. Again, each are the 2×2 block. Okay. Okay. So this is the gamma matrices we're going to use. And as we discussed before, there are many different choices of gamma matrices, and some of them are convenient for certain purpose, And as we will see, this one actually makes the non-relativistic limit more manifest. Okay, so it's conveniently reduced to a non-relativistic limit. And so in the rest frame, those equations simplify. Essentially, U just become the eigenvalue equations for gamma 0. Okay, so you find, say this equation for U. So let's denote the rest frame by 0, and then so the equation for U just become this in the rest frame, and the V given by this. Okay, so essentially this is just corresponding. Essentially, you see the U and V, U0 and V0, just corresponding to eigenvalues of gamma 0. Okay, because this is gamma 0 times U give you a constant. Okay, I can move that constant to the right-hand side. It just looks like an eigenvalue equation. Okay, and so you can just easily plug this in and easily solve them, which we already discussed last time. Say, for example, you find that there are two independent equations. So this is a 4×4 matrix. So gamma 0 is a 4×4 matrix, and actually have two eigenvalues. Say so each U and V have two, say, independent solutions. Okay, so you find that say, for example, one solution is just given by 1, 0, 0, 0, U2. So this we all discussed at the end of last lecture. Here I'm just trying to remind you. Okay, so in this rest frame, the solutions are particularly simple. And so essentially you have two independent solutions, and then you can take actually arbitrary linear superposition of them, because we are solving linear equations. Similarly for V, and you can take the arbitrary linear superpositions of these, and then you will solve them. Okay. And then for the for general UK and the VK, you can just perform a Lorentz transformation. So you can perform Lorentz transformation, say the UK is obtained by, say, S lambda UK0, U0, okay, and the VK is given by S lambda V0. Okay, so the lambda, so remember our notation S lambda is a Lorentz transformation on the spinors. Okay, it's a Lorentz transformation on the spinors, and the lambda is just determined by the Lorentz transformation to take this K0 to K. Okay, so for arbitrary, so we take this K0, so you make the Lorentz transformation to K, and then the corresponding UK, then it's getting by that. Okay. But in practice, if I give you an arbitrary, say, give you arbitrary K, and you first work out the lambda, then you have to work out this S lambda. So working S lambda is possible, but again, takes some effort. Okay, but there's still a lot of shortcut. We can actually find the solution. So this is one way to do it, and there's an alternative way. So before I talk about this alternative way, do you have any questions? So this is more or less where we stopped at the end of the before the break. Any questions? Okay, good. So alternative would be we can actually find a simpler way. So So the simpler way is by observing an identity, okay? Is that if you look at k slash square, so you have done something similar in your P set. Okay, if you look at the k slash square, so this quantity by definition is k mu, gamma mu, k nu, gamma nu. Okay, and then you use the properties of gamma mu and gamma nu, okay, and then you can easily convince yourself this is just giving you the k square. Okay, this just gives you the k square, and then because we are looking at the unshared solution, so this is just equal to minus m squared. Okay. Then this means that if I have ik slash plus m, so which so appearing in the equation for u and v are ik slash plus m or minus m, and then if I multiply by ik slash minus m, okay, and then essentially I have minus k slash square minus m square, okay, and this is actually equal to 0 because of this equation, okay. So now we can immediately observe, okay, so now we can immediately observe if I take a solution, if I just to solve that equation, we can just write u as, say, some normalization constant, n will be a normalization constant, and ik slash plus m. Okay, and then acting on some arbitrary, say, u tilde, okay, some arbitrary spinor, and then this equation, that equation automatically satisfied. Okay, automatically satisfied. And similarly, v, if I take some normalization constant, and I take minus ik slash plus m, say some v tilde. Okay, so that equation again, the v equation automatically satisfied. Okay, because of this identity. And now we know that there's only two independent equations, two independent solutions for both u and v. Okay, and for both u and v. So we can choose a basis for u, and just by taking this to be, say, us0, and then this would be a basis, a complete basis of solutions. Okay, so S will go 1 to 2. Okay, so because we have for each of them we have two independent solutions. Okay. And so the reason we can choose US here, you can also check that when you take the m, when you take the to be so when you take k to be k0, so you can easily check yourself that this this essentially just reduced to US0. Okay. Yeah, this is consistent. Yeah, just say when you take that, you just reduce to this basis. Okay. So n is a normalization constant. And so the US, VS, then provide a basis. Then this is a basis of solutions. Okay. And we can be sure these are the complete bases because that's the only, essentially we already know the solution at at the rest frame, and we just have the right number of the independent solutions. Yes.
How do we know the normalization constant is the same for u and v?
Oh, yeah. Here we don't know. But you can guess why it should be the same. It's just essentially, so this because the equation looks pretty symmetric, and the normalization constant don't depend on the sign of m. Essentially, In principle, I should write n1 and n2. But in the end, they are the same. Good. Any other questions? Okay, so you can also, if you take the conjugate, then you can get what's the U dagger or the U bar, or V dagger, V bar. Okay. So for example, you just take the conjugate, then you find the US bar. So I hope you still remember the notation, the US bar, which is a US dagger times gamma 0, and the US bar, okay. So this is for the conjugate solution, will be A, n, the same n. We can take n to be real, say US bar 0, then IK slash plus m, okay? So you just use the properties of the okay, so you can also find this. So now you can easily check yourself, okay, using this equation. You can check that the U bar and the V bar are actually, U and V are orthogonal in the following sense. And the U R bar Vs is equal to V bar R US is equal to 0 for arbitrary Rs equal to 1 and 2. Okay? So U and V are orthogonal. And we can also, and then we need to fix the normalization of U and V. Okay? So it's convenient to fix their normalization as follows. So we will use the following convention. Say US bar, K, say UR, K, U bar, and USK equal to IQM delta RS. Okay? And similarly, VR bar K and VS K equal to I minus I. QM. Okay, so this 2m just for convenience. Okay, so it just convention for convenience, and so you can check yourself that actually so different U, different value of R and S, they're also orthogonal to each other. You can already see already in the rest frame. Okay, you can just easily check. Using those expressions, but you can also check, again, using this identity, that the different value of R and S, they're orthogonal to each other. And when they are the same, and then we normalize the constant to be 2m. Okay? And from here, you deduce that n is equal to 1 over square root E plus m. So from now on, I will also use this notation for E. So the E, the energy, is omega k. Okay, so now I will also use this notation. Okay. Good. So this gives you a complete basis of solutions to the Dirac equations. Okay. So now let me just write them down to give you a little bit intuition about the explicit expression. So with those gamma matrices, we can just plug in here. Okay. And we know what's US0, VS0, we know n. So in principle now we can write them down explicitly. So you find that in that basis, then the USK is given by the following. Given by the square root E plus M psi S and the sigma dot K divided by square root E plus M psi S. Okay, and the Vs K is given by sigma dot K divided by square root E plus M, also psi S, and E plus M psi S. Okay, and psi S is a 2, so S from 1 to 2. And psi 1 is, so psi S are 2 component vectors. One is given by 1, 0, and the other is given by 0, 1. Okay? By 0, 1. So that you get. So you can see in the rest frame, K equal to 0, essentially for you, you just left with the upper half because this is 0, and then we have the 1, 0 and the 0, 1. Okay, and then when K equal to 0, and for V, you just left with the lower half, and again we have the 1, 0 and the 0, 1. Okay, and so this is consistent with the rest frame result obtained earlier. Good. Any questions on this? Yes.
What's sigma?
Oh, sigma just the sigma matrix. So this sigma just Pauli matrices. Sigma 1, sigma 2, sigma 3, Pauli matrices. Yeah. Good? Good. Okay. So let me just make a few remarks on the solutions, and to be familiar with the properties of the solutions actually will be very useful when later you do Feynman diagram calculations, because the different, when you involve, say, electron fermions, and now it's no longer a plane wave. Okay, so this U and V will enter your Feynman diagram calculations, and if you are familiar with their properties, and will help you to do such calculations. Okay, so let me just first mention some properties. Make some remarks. So first is that if we consider the non-relativistic limit, okay, the non-relativistic limit, so that's corresponding to you take the magnitude of K divided by M goes to 0. And then in this limit, E would be approximately equal to M. Okay, approximately equal to M. And then you find the leading order when you expand, say so you can expand this in 1 over M. So at the leading order, you find that the USK, so you can just easily do this too, okay? And so this term certainly you can just ignore because E, so this is M, so this is K divided by square root M, so this is higher order than this one. And here is the square root M. So to leading order, you have square root 2M, psi S is 0. Okay. Similarly, VSK equal to square root 2M leading order, 0 psi S. Okay. So essentially, what you see in the non-relativistic limit, for example, if we look at these positive energy solutions, so this is just reduced to arbitrary. So USK, now you can do linear superposition, just UK, just reduce to arbitrary two-component complex vector. Okay. Yeah. So you just this is just some constant, and as a basis you just have this basis, and then you can just now do arbitrary. Just become the arbitrary complex vector. So this should remind you how we describe a spin half particle in non-relativistic limit. Okay, in the non-relativistic limit, the way we describe a spin half particle, and it's precisely a two-component vector. Okay, so this is exactly as the description of a spin half particle. Yeah, the wave function. Here you should understand as the wave function description of the spin half particle. Okay, in non-relativistic quantum mechanics. Okay, and so I will not go through here, but you can show in the non-relativistic limit, this solution actually decoupled. Okay, in the end, when you solve the equation, only one half of the equation, one half of the solution remain. And actually, this is no longer, you just get the positive energy solution. So, so in that limit, you essentially only reduce to two components. Okay. So this is the first remark. So this is the first indication. We see that this should likely describe a spin half particle. Okay, the Dirac theory likely describes a spin half particle. So the second limit we can consider is consider the ultra-relativistic limit. Okay, so this is a limit which E is much greater than, energy is much greater than M, okay, and E, and then will be approximate, say, to K, to the magnitude of K, okay. And now let's also define the direction of K by just K divided by its magnitude, okay. So we also introduce the K hat. It's a Euler vector along the direction of the K. So in this case, you can do a small m expansion. Okay, just do a small m expansion, these two expressions for V, U and V. And then you find the leading order, USK given by square root E. Okay, and then you have psi S. And then you have sigma K hat psi S. Okay, this is for the US. And for the VS, you find so that's the so you find that solution simplify, and so that's the result you get. Okay. So it's not manifest from this expression, but actually there's something very special in this simplified expression in the ultra-relativistic limit. So if you look at the expression for U and V, these are linearly independent. in the sense that no matter how you do linear superposition of u, you will not be able to get v, okay? And also how you do linear superposition of v, you won't get u, okay? But in this limit, even though it's not clear, not manifest in this form, but in fact, these two are linearly related to each other. So this can be seen as follows, okay? So if you use the identity, that's sigma dot k square. Okay, so this is the analog of this equation for the sigma matrices, okay, for the Pauli matrices. And this you can easily, again, using the property of Pauli matrices, you can convince yourself that this is just giving you k hat square. Okay, give you k hat square. And this is actually, because this is a unit vector, this is just 1. Okay, so now if you use this property, this is equal to 1. And then we find, and then net eta s equal to sigma k, sigma dot k hat psi s. And then you find that the vsk can be written in the exact form as usk. You just replace eta s by psi s by eta s, and then you can have it in the following form: square root e eta s sigma dot k eta s. Okay? So it's obviously this is equivalent to that. Once you plug in the eta s equal to sigma k psi s, because this just gives you that. And when you plug into here, you get the sigma k square, and you get 1, and again you reduce to that. Okay? But now these have exactly the same form as this one, except now eta s is a linear superposition of the psi s. Then that means that the vs is a linear superposition of the us. Okay? So this means that the vs is a linear superposition of vs. So vs now is a linear superposition of vs, of us. So they are no longer independent. Okay, so they are not linear independent. Okay? So actually, if you remember one observation we have discussed before, this may not appear a surprise to you. Because previously we already discussed when we derived the Dirac equation. So Dirac equation, in order to satisfy all the properties for non-zero M, we need 4-dimensional matrices. Okay, so that means psi is a 4-vector. But we also mentioned that if you, in the massless case, set M equal to 0, in the massless case, actually you can use 2 components. Just use gamma matrices. So that means that if you solve a massless Dirac equation, you only have 2 independent solutions. And this ultra-relativistic limit is precisely like the massless limit, because the mass, the energy is much greater than the mass, and then you can neglect the effect of mass. Okay, so this is consistent with that the massless Dirac equation can you say with that the only requires two components, okay, rather than 4 components, okay? Yes?
So in the ultra
Yeah, that you have to be a little bit careful. Yeah.
So does that mean that's not to be thought of as like an inner product on the spinor space?
Yeah. So that's a very good question. So you have to be careful a little bit, and when you take the limit in deriving that relation. Yeah. Just you have to be a little bit more careful in understanding. Yeah, I forgot the exact what exactly happened to that equation, but I remember there's some subtleties. Yeah, you have to be. Yeah. Mm-hmm. Good. Other questions? Good. Okay. So also there are some other useful relations which will be useful later. So one of them. So let me also list some useful relations. So one is that if you look at UR dagger and US, so this is K, US K. Okay, again, this is orthogonal between R and S, and then it's given by 2E dot RS. Okay, so here is bar, so the difference here is bar. And so when you have a bar, you have additional gamma 0. Okay, and then here is 2m, then here become 2e. And here you have additional I, it's because you have a gamma 0. Because gamma 0, remember gamma 0 squared to minus 1. So gamma 0 have actually eigenvalue to be pure imaginary. So that's why there's a difference in I here. Okay. And similarly, the VR dagger K and the VSK equal to 2E dot IS. Okay? So those expressions to will be very useful later when you actually do calculations. Oh, right. Yeah, I forgot to mention. Yeah, the reason is that the reason that the limit is subtle when you do that is because remember the normalization we do here is M. So so you have to change your normalization when you go to the massless case. Yeah. So there's various things you have to be careful. Okay. Various things you have to be careful. So you have that, and then you also have the relation that the UR dagger K, so because everything is on shell, so in principle I only need to specify the spatial momentum. Okay, so for convenience, let me just specify the spatial momentum, and which is easier in notation. So now it turns out UR and the VS. So now it's the dagger. When you have bar, they're orthogonal. We have expression there. But when you have dagger, it turns out it's orthogonal to minus K. Okay, you have to reverse your spatial momentum. Okay, and this is equal to VR K and US minus K. So this is equal to 0. But this is actually not equal to 0, okay? UR dagger K US VS K is actually not equal to 0. Okay, so they are not orthogonal. Okay, only the bar relation is orthogonal, and then this relation is orthogonal. Okay. And similarly with the conjugate of this. Okay. So those relations, you can just check them using explicit form of those expressions, okay? And we have this expression here. You can just check those expression is true, okay? And so we are not going into that. But actually, more remarkably, those expressions, so when we derive this expression, we actually use the explicit form of the gamma matrices, okay? It depends on the explicit form. So those expressions depend on explicit form of these gamma matrices. So if you have a different set of gamma matrices, then you get different forms, okay? But of course, physically, they're all equivalent. But it turns out that those relations, okay, so those relations actually are independent of choice of gamma matrices, okay? So, so let me just label them by, let me call it star, and here by star. So star and star are actually independent of choice of representations of gamma matrices, okay? So they're actually universal for any choice of gamma matrices. So this is very useful, okay? Because when you do calculations, then you don't have to worry which choice of gamma matrix you make, and those expressions are true. So you can actually derive those expressions, okay, without using gamma matrices, just abstractly, only using the properties of the Dirac equation itself and the general properties of gamma matrices without using explicit representations, okay. Yes?
So is the other normalization one dependent on the representation?
Which one?
The one with the U bar V?
No, that also does not depend on representation.
Okay.
Yeah, that also does not. Yeah, all this normalization does not depend on the representation. But this expression somehow is, yeah, that's just our definition. We just define them this way. So this just follows from those general expressions from this equation. But this equation is less obvious because without gamma 0, then it's less directly related to the Dirac equation itself. And it turns out this expression also independent of the choice of gamma matrices. Okay. Any other questions? Okay, I can give you a derivation of this without using gamma matrices, and yeah, but that take a few minutes. I will skip that. You can read it in Paskin. So Paskin has a derivation of this. Okay. Good. But you should remember this yourself. Okay, just remember it. Good. So the fourth remark is that often we actually need to use the projection. So you can also construct projectors to the positive and the negative solution space, okay? Spaces. So so consider, so the projector to the space spanned by US can be defined as the follows. So let me call it P plus. So this is just from QIM, so that comes from the normalization. Then just sum S equal to 1 and 2. USK and US bar K. Okay? So you can easily check yourself, okay, because of those orthogonal relations, or because U and V are orthogonal. When you act this on the general solution, we'll just project into solutions proportional and only involve linear superpositions of U. Okay. So now you can check yourself explicitly. Let me erase this. So just use property of this U. You can check yourself explicitly, which I will not do there, and you can check that this is indeed a projector. Okay. If you look at P square, it gives back to itself. Okay. And with a little bit more effort, you can further show that the P plus can be written in the following form: IK slash plus M divided by 2M. Okay? So this requires a little bit more effort, so I will leave as an exercise for yourself, okay? Or you can get it from the books, okay? Yeah. And similarly, you can define the projector to the space of V. So the P minus, you can also define P minus to be minus 2im because of the minus sign here. So 1 over minus 2im sum S VSK Vs bar K. And you can show that this is also can be written as something like this: minus IK slash plus M divided by 2M. Okay? So again, this I will leave as an exercise to yourself. So this is a projector to the space of V's, and then from this two expression, P plus, P minus, you easily see that P plus plus P minus equal to 1. And use the expression I just erased. So from taking the product and the P plus P minus is equal to P minus P plus equal to 0. Okay. So indeed, they are just projectors, orthogonal projectors into different space. Okay. So this concludes our discussion of the classical solutions of Dirac equations and their properties. So do you have other questions? Yes?
So we've seen hints that these represent spin one half, but wouldn't it make more sense to just define the angular momentum operator and see whether it has eigenvalues or not?
Yeah, that you need to quantize the theory first, right? But we haven't quantized the theory. Yeah, so yeah, that will be our next step. So once we have found the full set of classical solutions, and now we can quantize it, and once quantize it, then we can actually really find this angular momentum. Yeah. Other questions? And indeed, actually, I think that would be one of your p-set problems. Yeah, to show yourself that this is spin half. Yeah. Yeah, but other questions? Okay, good. Good, so now we conclude the discussion. Now we can quantize the theory. Now we can go to the quantum system. Okay. So remember the action for the Dirac is d4 x psi bar gamma mu, partial mu, psi, partial mu, minus m, psi. Okay? So this is the action which gives us the Dirac equation. So in order to quantize it, we first remember our procedure to quantize a theory. So we need to first find the canonical momentum, and we also need to impose the canonical commutation relation, and then expand your operators in terms of a complete set of classical solutions, and then that's corresponding to the solutions to the operator equations. Okay, so let's try to find out what's the canonical momentum of psi. So as in the complex scalar case, we can treat the psi and psi dagger as independent variables. Okay, because of the So then the canonical momentum for psi, if you look at this expression, so you look at the partial zero on psi, then you find, so the Lagrangian density, if you look at that, if I write it, have the form psi dagger, so this psi dagger, gamma 0, and then gamma 0, psi 0, psi, then plus the rest of the terms. Okay, so in order to find the canonical momentum, we are only interested in the part of the Lagrangian density which are related to the derivative of psi, or the time derivative. Okay, and then, so that's the only term involving time derivative of either psi or psi bar or psi dagger. Okay, so this gamma 0 square equal to minus 1. So this is just I psi dagger partial 0 psi. So now we can immediately find out that the conjugate momentum for psi is given by I psi dagger, because you take a derivative on psi 0, partial 0 psi, you just get I psi dagger. But the conjugate momentum for psi dagger is actually equal to what? So what is this? This is equal to 0, because there's no time derivative on psi dagger. So this tells you, okay. So fact that this equal to 0 tells you actually the Dirac system. Okay, the action. This Dirac system is actually a constrained system. So this is considered to be a constraint. Okay, because you can no longer normally. So remember, when you when we say from the Lagrangian, you find the canonical momentum, and then you invert the canonical momentum to find the Hamiltonian. Okay. But when you have this equal to 0, you cannot invert it. Okay, you cannot express your, say, psi or psi dagger in terms of pi psi dagger. Okay, and so this is a constraint. So that means you actually have a constrained system. Okay, means you have a constrained system. And frankly, constrained systems are very annoying. Okay, very annoying. And they have involved lots of formalism in order to, say, treat the constrained system, to quantize them, etc. Okay, but fortunately in this case there's actually a simple trick to go around it. Okay, and so now I will not use this full-fledged constrained quantization to do the job. I will just use a simple trick which will reach the same answer. Yes. Yeah. So there's ambiguity. So that's part of the reflection that this is a constrained system. Yeah. So this is actually typical to have this kind of constraints. It's typical whenever you have a first-order system. So here it's different from the Klein-Gordon action is because here it only involving the first derivative, okay, one derivative rather than two derivatives. And so this is not our standard system. Okay. So the way to go around this is the following. Okay, the way to go around is the following. Is now, so this equation, if we look at this equation, so this equation tells you that the canonical momentum conjugate to psi is actually psi dagger. Okay? So also here it's a little bit funny, because remember in the standard story, the canonical momentum is related to the time derivative. Okay? And here there's no time derivative here, just psi dagger itself. Okay? And this is another indication that this is a constraint rather than, yeah. So anyway, so here tells you that the psi dagger is in fact the canonical momentum to psi. And now we can just, now in this equation, we can just try to interpret the psi dagger as the momentum rather than as a configuration variable. Okay, so now let's rewrite the Lagrangian. So the Lagrangian has the following form: minus I psi bar gamma mu partial mu minus m psi. Okay, so this is the Lagrangian density. So we'll rewrite it as the following. So let's first separate the time derivative. So this is psi dagger. So just this term involving the time derivative. And then the rest, I have psi bar gamma I partial I minus m psi. But here they're no longer involving the time derivative. And now we just interpret this as the canonical momentum for psi. Okay? And then this is just something involving spatial derivative of psi. And I just interpret this as a Hamiltonian for psi. Okay? Okay? So this expression just involving psi dagger and the psi, involving some spatial derivative. So this is essentially just some functions of psi, pi psi and psi, and maybe with some spatial derivatives. Okay? So now you see that this Lagrangian density, actually, if I interpret the psi dagger as the canonical momentum, then has the form of this canonical transformation to go from the Lagrangian density to Hamiltonian. And then I can just interpret this as a Hamiltonian. Okay, I can just interpret this as a Hamiltonian. Okay, so now I can just interpret this as my Hamiltonian. Okay? So we just treat so now we just, so this is, so psi dagger and psi, and now this is the full phase space. Okay, so this is the momentum, and this is the coordinate, so this is the full space, okay? Rather than previously, we would interpret them as a configuration space, okay? We interpret them as configuration space. And then the Hamiltonian just equal to I psi bar gamma I partial I minus m psi. Okay? So this is the Hamiltonian density. Okay, so we now then have, now this just go back to the standard formalism. Okay? Any questions on this? Yes?
So do we still interpret psi dagger as a different field than psi?
As its canonical momentum.
Okay. But so it's no longer like two different fields.
Yeah, it's no longer two different fields. For example, if we have two different fields, then psi and psi dagger, they should commute.
Right.
But now, since they become canonical momentum, they no longer commute. Yeah. Yes?
If you take psi bar and you pull out the gamma zero, isn't this just like the right hand side of our earlier version of the Dirac equation, the one where you how do I explain this? Like the one with like alpha and beta, like the other Dirac equation we wrote that earlier.
Yeah.
Okay.
Yeah, that's right. Yeah. It's very, essentially just that Hamiltonian. Yeah, that's right. Yeah. Yes.
Is there not a problem with this, like treating the time differently? Like, is it no longer Lorentz invariance?
Yeah. So when we do the Klein-Gordon equation in the scalar theory, when you quantize, you always have to treat time differently, and then the Lorentz symmetry is come out in the property of the states, right? Yeah, but you always when you quantize, you always have to treat time separately. Yes.
So now we have the momentum operator. It's just the complex constraint of the position.
Yeah, exactly.
So it's still like constraint like what?
Yeah. This just So that's why we call this a constraint system. But now I'm just giving you a shortcut so that we have to don't have to go through this. The intricacy of constraint quantization. Yeah. Okay. So now the canonical quantization become easy. So now this is my momentum. So now we just have the canonical quantization. I think today we may have unfortunate timing. So now become psi is coordinate. And now we have psi dagger, we have pi psi, which is the momentum. So this definition, by definition, should give you, say, the delta function. So equal time correlation function. So here we should, because remember this is a 4-vector, so this also have 4 components. So let me just now suppress this subscript psi because there's only one variable here now. So here there's also coefficient. So this is also 4-vector beta, and then here should be delta alpha beta. Okay. So alpha beta are spinor indices. Okay, are spinor indices. So if you impose and this is equivalent just to psi alpha tx psi dagger beta tx prime equal to I delta alpha beta x minus prime. Okay? And so we can now expand psi x in terms of complete set of solutions. So this is the first step of the quantization. So first is this is the commutation relation. So the second step, remember we can expand the psi in terms of complete the basis of classical solutions. So psi x just equal to, again we integrate over all spatial momentum. Again we use this factor for convenience as in the scalar case. And now we just need to sum over all possible solutions. So here we have a sum over S equal to 1 and 2. Okay, so we have AK S US IKX, and then plus the BK, sorry, K should be here, sorry, BK S and VS exponential minus IKX. Okay? So these are the complete, because the complete set of solutions are U and V, and we call the coefficient of A and B, so let me call it B dagger as we did for the complex scalar case before. Okay? So the coefficient, we call them A and B. Actually, it doesn't matter we call it B. Actually, let me just call it B. Okay? Yeah. So you can just, you have U and V, and then the coefficient will be A and B. Okay? And so now you can just plug this. So if this equation is 1, and this equation is 2, and you take the complex conjugate Pythagoras, you can plug in here to find what's the commutation relation between A and B. Okay? So you find that the so plug 2 into 1. So you find the commutation relation. Okay, AK S AK prime T then equal to BK S and BK prime T then equal to 2 pi cube delta ST delta 3 K minus K prime. Okay? So now, and you can also define the vacuum. You can also define the vacuum. So, and all other commutators are 0, okay? With all others 0. Okay, so, and you can also define the vacuum as we did for the scalar case to be annihilated by AK and BK okay? And now you can, in principle, build your Hilbert space. Okay? Yes?
For equation 1 up there, are you supposed to have that factor applied? Just because momentum is psi dagger, right? So,
Yeah.
and then
Oh, right. Sorry, there's no. Yeah, thank you. There's no I here. Yeah, because the momentum is I psi dagger. Yeah, there's no I anymore, just the delta alphabet. Okay, so all look pretty straightforward. Okay, but you actually have problems. Okay? You actually have problems. So the first problem, some of you may be already asking. In your head, you said, are we supposed to describe spin 1/2 particles? But if we are supposed to describe spin 1/2 particles, then why do we find the bosons? Okay, so these are commutation relations for bosons. Okay, because they commute. Okay, so different k, they. Sorry, I think I'm missing dagger. Sorry. So different ak, they commute with each other. As we discussed in the scalar case, when the A mu all commute with each other, this is boson. Means the particle you created, you can exchange them, and don't. Yeah, you can arbitrarily exchange them. Okay, it's symmetric. But fermions, they're supposed to be Pauli principle. Okay, so you're supposed to get a minus sign when you exchange them. So this doesn't look to be right. Okay, so this is the first thing seems to be we will find in bosons. Okay, rather than fermions. And the second is that now if you find the Hamiltonian, so now if you try to find the Hamiltonian, so H is just integration of the this Hamiltonian density. So and you can just plug it in. Okay, plug that expression for Hamiltonian density in. Where is my Hamiltonian density? Yeah, plug that in. Okay, and then you will find the yeah, so you find just this just given by I d3x psi bar gamma I partial I minus m psi. Okay. So now if you plug them in, okay, you just plug them in, plug this mode expansion in, and then you find actually. Okay, then you find the following expression. Omega k, and you sum over S from 1 and 2, and then you find it's given by AK S dagger AK S, okay, minus BK S dagger BK S. Okay, and then up to some infinite constant. So now you see something problematic here. So what's problematic you see? Yes? Yeah, energy is not positive definite because of this minus sign. Okay? Because this minus sign. So this minus sign tells you that if you excite a lot of these B particles, you can make the energy as selective as you want. And then the theory don't make sense, okay? And then this is a theory with energy unbounded from below. Okay, it's a theory with energy unbounded from below. So that means this vacuum is unstable. Okay, the vacuum is unstable. Okay. So there must be something wrong with this procedure. Okay, something wrong with this procedure. So it turned out that there's a very quick fix to this problem, and this quick fix was invented by Jordan. So he recognized that if you don't do the standard commutation relation, okay, if you do instead of commutator, here you change it to anti-commutator. Okay, remember this bracket, this curly bracket means anti-commutator. And that means that here you change it to anti-commutator. Okay? And then still with the same thing. Still with the same thing. And now, this becomes anti-commutator. Okay, so let me see. I just want to make sure I get the. Yeah, we change anti-commutator. Also from the convention, you change this to dagger. Okay, now you change this to dagger as we did for the complex scalar case, and then you just get this. And now if you do that, and then this becomes plus sign. Okay, and now this becomes plus sign. And now, not only this becomes plus sign, and also all different AK for different S and T, they anti-commute with each other. They anti-commute each other. So anti-commute each other means that if you create a particle, for example, AK dagger, and you create another particle, AK prime dagger on 0, and now these two anti-commute. Means when you exchange order, you get the minus sign. That precisely give you the minus sign in the Pauli principle. Okay, in the statistic for fermions. And so, so changing this thing to the anti-commutator, and so solves all your problem. And your energy now expanded from below, and then you actually describe some particles which obey the Pauli principle. Okay, which obeys the Pauli principle. So yeah, I think we still have 1 minute left, but it's a good time to stop because otherwise other things will take more time. So let me just make a couple remark why the commutate, why here you need to do something unconventional. Okay, why you have to do something unconventional. So if you look at this Hamiltonian density, so even without doing this calculation, okay, you can already conclude from here that this H cannot be bounded from below, okay, for the following reason. So from the Dirac equation, yeah, let me just erase here. So from the Dirac equation, you have gamma mu, partial mu, minus m, psi equal to 0. So that means that the gamma I, partial I, minus m, psi, is equal to minus gamma 0, partial 0 psi. Okay? So now if you plug this equation into here, and then what you get, you should find that H is equal to I d3x psi dagger partial 0 psi. Okay, so because the psi now this becomes an operator equation, and psi satisfies this equation, and now you find H become this form, and which is psi dagger times the time derivative of psi. And time derivative of psi, remember, psi it expanded both in terms of the positive energy solutions and the negative energy solutions. So depending on which omega you have, you can have either positive omega or negative omega. Okay, because this is the first derivative, first time derivative in psi, and so this cannot be a positive definite. Okay, so this quantity cannot be positive definite. anyway, so you have to do something more radical, okay? If these are conventional functions, and then this won't be positive definite. But now what we did is that we make this into functions which anti-commute. When the anti-commute, turns out this to be a positive definite quantity. Okay, as an ordinary function, this cannot be positive definite. But if the anti-commute, then become positive definite. Okay, so let's stop here.